All right. So today we have Angela who works on torch.export, and she's going to talk about this new tool that we have called draft export. And just to give some context, export is a tool that gives you graphs from models using the PyTorch compiler. However, it's an ahead of time graph capturing mechanism, and you can get errors. So the normal workflow of export works by basically giving you one error at a time. But a lot of users asked us whether they can get all errors at once and somehow manage to get a full graph. So that's where draft export comes in, and I'll let Angela talk all about it.
Thanks, Vic. So yeah, I'm going to be talking about draft export. And so, uh, example that Vic was talking about. So here I have this piece of code that it's just like a dummy function. But let's say I have this model, and then we have this like custom operator that does like pre-processing on it. And some reasons why it might be a custom operator is because it could either contain some like C++ logic, or it contains some like other mysterious logic that like you don't want to include inside of the model itself. You just want to hide it away in a black box. Um, and then afterwards, we have some like other random piece of code in the model that I just put together so that it will error correctly. So if we run this piece of code, it gives us, some tensor values. But if I try to export, so this is the API for exporting. It takes in the model and then the sample inputs in a dynamic shape specification, saying whether or not like we want some shapes to be dynamic. And in this case, I've marked the 0th dimension of the first input to be dynamic. So in this case, we have size 6, but I want to say that in other cases, we could all be also passing in values of size like 7, 8, or 9. And so this is why I marked it as dynamic. But for the second value, I don't want it to be dynamic, so I just marked it as none. And so maybe you like came across this model and you want to try to apply export on it. And so if we try to run it, uh, oh, I didn't say. The first thing that happens is no fake info registered for preproc. So what this is, so for every custom operator, we must have this thing called a fake implementation registered for it. This is because while exporting, we use this thing called fake tensors to help us trace through. And what it does is just records the shapes and D types that go through the method. And so in this case, to tell us how to get through preproc with fake tensors, we must have like a fake tensor implementation. So let's say that we add it. Register fake mylib.preproc. And um, yeah. So our fake tensor implementation can be exactly the same as the original implementation because all it needs is to tell us like how do we propagate the shapes and D types. But we could also just return like a dummy tensor with like the same shape. But in this case, like it works if we just return the same thing. So now that we have the fake im oh, sorry. So now that we have the fake implementation, we run it again, and we have this new issue, which says could not guard on data-dependent expression, U0 divided by 3 plus 5. And if we make this error a little bit bigger, we can see that it occurs on test.py on line 22. Um, what else does it tell us? And I guess it doesn't really. Based on the fact trace, we can see that it's going into this slice function inside of PyTorch, and there's this guard here that checks whether or not end val is less than 0. Um, and so we can kind of uh, think about it and see that this is checking to see that if whether or not this value A is greater than or equal to 0. Because when we can slice with negative numbers or we can slice with positive numbers, and and the behavior of the uh, slice operation could change depending on this. And so we just want to tell it that A is actually greater than 0. So here I will add a torch check that so to do this, I will actually add a torch check that A is a size value. And this will automatically tell it that A is being used as like the value for a size and that this is like greater than or equal to 0. So if we run it again, um, we can see a new one which says U0 it must be whether or not U0 is greater than 12. And so if we look at the stack trace a little more, we can see, okay, there's some line here that says like statically non-true, something, something, and
So the 12 comes from the cat operation right before.
yes.
Yeah, so
Yeah.
66. Okay.
Yeah. So from just looking at this error, it's a little bit complicated and we can't really tell like where this expression is coming from, where the 12 is coming from. The still on the slice again. And so it's like a little bit annoying, but actually the correct solution here is that we need to add a check to make sure that A is less than the shape of Z. Um, and so after we run that, we actually run into this constraints violated error, which says that we marked seq length as dynamic, but our code specialized it to be a constant 6.
Yeah, I was wondering about that because the moment you said you wanted to do dynamic and then I saw the assert in there. Uh, that's sneaky.
Yeah. So I was trying to I was trying to demonstrate that like sometimes
Yeah,
inside of
yeah.
a code, yeah.
Yeah,
Um,
I mean the real life scenarios modeling is that you haven't really looked at the source code of the model, or in general the assumptions in the model might be baked in pretty deep, and
mm.
you're just trying out your mental model says that something should be dynamic, but you don't know whether it's going to work or not.
Yeah. So if we comment this out, because maybe like this assumption isn't true, or like we don't actually want this assumption, then we can export the model and yay, it gives us an exported program. And so we see the call to preproc, we see like the add, the mul, or sorry, the divide, and we see the cat and the slice. So yay, it worked. But that was like a pretty tiring experience, right? Like we had to write a fake kernel, we had to understand all of the guards and then add these checks and then like also like delete the assert. So in this case, like the assert was like pretty easy to figure out, but in some cases it's like a lot harder. And so in some cases, users really just want the graph itself. Like, what if we're just trying this out? We just want the graph to play around with to see, like, to bring it to the rest of our workflow. And we don't really care about all of these correctness, like whether or not, like, x of that shape is like actually equal to 6 or something like that. And so what if like we just really wanted a graph? And so this is where draft export comes in. So draft export is a version of export which will always successfully export a graph, and it will bypass any of like the previous export errors. And instead, these errors will be compiled into a report for a clear visualization, which you can then later address maybe after you're done like bringing the graph through your pipeline. So what are the types of errors it catches? Here is a chart of like an estimate of torch export errors. This is not like an actual like representation of everything, but sort of like a compilation after like running through a bunch of internal models and looking at a bunch of GitHub issues. This is sort of like the estimate of what most people run into. And so a lot of it is like missing a fake kernel, guard on data dependent errors, or like constraint violation errors. There are also some other errors, such as like missing a PyTorch registration, missing like or having an attribute assignment, or some other random things. But draft export will be able to catch these set of errors, which are actually like 90% of most of the errors that export users will run into. And for the other ones, we are looking into how to fix them, but sometimes like we're not actually able to automatically fix them for you. So they might
Just
result in some, yeah.
Yeah, so just to be clear, so if you do get some of these other random errors, what will happen? So draft export will fail to produce a graph in that case, right?
Yes, and it will error the same way that normal export would error.
Right.
and it might require you to like actually fix the model or file an issue on GitHub.
Yeah.
Yeah. So how does this work? So this is how a normal tracing looks like in normal export. So we have the error code here. It calls like preproc item, all of this stuff. And every time we call an operation, the tracer will record this operator inside of the graph. So when we call preproc, this corresponds to like the mylib.preproc call. Calling item will go into item, and then calling cat will return like a a10.cat into the graph, and like slicing will have a slice in the graph. But at the same time as the tracer runs, we run it using fake tensors to help us record all of these nodes. And the fake tensor just stores like the shape and D type of what this operator returns. So in the preproc case, we're returning something of shape S0. This means like S0 is just like a symbolic size. And in the case where we have this y dot item, we return this U0. U0 means this is unbacked, meaning we don't actually know what the value behind it is. Oh, sorry,
I
I
see.
forgot to mention.
So
Yeah,
S0 was the shape of the input,
yeah,
but you mentioned it's dynamic, and therefore we create a symbol for it. Except that we know that the backing value for that is 6, but for U0 you don't know that.
yeah. So fake tensors are just tensors that do not have any values behind it. So when we do item.item, it's trying to inspect like a value inside of the tensor. But because we're running with fake tensors, which don't have actual values, we don't actually know what the value is there. So we have this U0, which doesn't have a backing behind it.
Mhm.
Yeah. Um, and when we do like a divide by three, in like we just store this entire expression of U0 divided by three, and this plus five creates like this even longer expression. And then once we get to the slicing call, what happens is we see a check for whether or not this value is greater than zero and whether or not this value is less than the shape of Z. And so this will then turn into checks for whether or not U0 is greater than zero, or if this expression is like less than this other expression. And in this case, since we don't know how to evaluate this expression, we will throw a guard on data dependent error. So I guess by the name, it says there's this data dependent behavior of this U0 because it's dependent on the data we've provided. And we couldn't figure out how to resolve this. And so we've errored. Um, and so in the case of draft export, what we do is this thing called real tensor tracing, where every time if we run the values with fake tensors, we also run it with real tensors that we took from the sample inputs. So now U0 will have now a fake backing behind it, which is the sample inputs we pass in, which is 2. And then we will be able to evaluate like all the other expressions. And so when we get to this, whether or not U0 is greater than equal to 0 check, we will just plug in that 2 that we had from our sample inputs and then evaluate this to be true and then evaluate this other expression to be true. So in this case, S0 already has a backing, which is 6. And so this expression can also be evaluated. And then we can continue running and actually get the graph.
Cool. So from what I understand here is that the graph would still be generalized with respect to S0, but now you're like specializing the graph to the case where y dot item was exactly 2. Um,
Yeah. So if in our sample inputs we passed in -1, then this expression would evaluate to false, and then we would take a different branch down the graph.
right, right.
So in the case where we reach a guard that we cannot evaluate, we just use the fake tensors behind it to help us evaluate it, and that helps us bypass all the guard on data dependent errors. But for the missing fake tensor errors, what happens is if we have an operator that doesn't have a fake implementation, then we will just run that operator with the real tensors, get the output tensor from that, and then return in our fake tensor implementation another tensor that has the same rank, but with unbacked shapes. So we just say like, we know that this tensor will be of rank 2, but we don't actually know what the shape is because it could be dependent on what your inputs are. So we just return unbacked shapes again. So the graph that gets created by draft export is guaranteed to work on the given sample inputs that you've passed in, and it's specialized on that sample input. So depending on which branch it takes based on those sample inputs, and so it might not necessarily work on any other inputs. And to show that, we also add in asserts into the graph so that if you do run it with other inputs, it will error and tell you that this graph has not been made to work for these types of inputs.
But if you were lucky, the certs would still pass, even if the data was a little bit different. If you were not depending on the exact values, then it would still be fine. Yeah.
Yeah, yeah. Yeah. So then what does draft export look like? Well, what happens is we can just replace the export call with draft export, and they have the same signature. And so in the case where draft export succeeds, we will return an exported program, or I guess most of the time draft export should succeed, and then we will return an exported program. And in the case where there are no errors, then the behavior will be exactly like export. But in the case where there are errors that draft export has bypassed, we will see this terminal output that says like, hey, 4 issues were found, and then please, you can view the report of all the errors with this TL parse command, or by printing it out if you're in like a Python setting. So let's go back to our example here. And let me comment out all of these fixes that we did. So if we run this again, it should error with the first error that we encountered, which is the no fake impl. And if we replace this with draft export, we now get a graph. Woo! And we can see in the output like 3 errors were found. Here, please run this command, or we can directly print it out with this. And there was another issue that we found, which was that an operator doesn't have a fake kernel, but we'll get to that later. So if we print out ep.report, this will contain a report of all of the issues that we encountered. So the first thing is we were missing the fake kernel, which we bypassed. And then we had a data dependent error for this uh, assert x is equal to shape 6. So in this case, it's considered a data dependent error because we replaced this fake implementation with another implementation that just returned tensors of unbacked shapes. And so when it checked the shape, it was unable to determine whether or not this value is equal to 6. Um, so it's labeled as a data dependent error because of the fake implementation that was used to bypass the first fake implementation.
Mhm.
And then later we have another data dependent error for the slicing operation here. So the alternative is we can use TL parse. So while we're
Okay,
running draft X, yeah.
but this is already like less than equal to 0, or that error is already better.
Yeah.
The error message is already better because it tells you, yeah, the locals and so on, and what actual value. So it tells you that A was that expression, right?
Yes, yeah. Yeah, so the error here also like shows a little bit more information, like it clears up all of the errors like logs that we saw before to just extract out this slicing to show that this was actually within the framework code, this is where it erred, and then here are some of like the locals information. So this expression corresponds to what A is here. Yeah.
Yeah.
So while we're draft exporting, draft export also returns this log file of everything that has occurred. And so if we use TL parse by just doing TL parse here like that, and actually, so if we run TL parse, this will generate an HTML report for us to view all of the errors in this nice HTML file. And in our case, internally, we can actually get a nice HTML file, like website for us. But in open source, you'll have to like load it up onto your Chrome page. So what the TL parse report looks like is something like this, which lists out all the errors that occurred. And for errors like this data dependent error, we can then click more into it. And it'll show us a little bit more information than what the print of the report did. Specifically, it'll show us this provenance information, which tells us where each value came from. So this U0, it shows that it came from the .item column. And the U0 divided by 3 came from this divide by 3 operation. And this 5 came from here. And then finally, this like less than check came from the slicing code here. So hopefully this should give you like a better sense of how um, the guard was created so that you can help add checks for this.
Yeah, this is cool because most of the time when you see guards, internal guards being dumped into the terminal, you have no idea how they were created. So this basically breaks it down. Hey, I had a quick question. So what happened to the greater than 12 or less than equal to 12 thing?
Yeah, so all of that is within this one slice operation. And so there's like multiple guards that are occurring inside of the slice. And to, not clump up the terminal with like too many things, we just merged all of the guards that occurred on the same
Ah,
line. Yeah.
okay, I see.
So like after fixing this error, if you run draft export again, the 12 should show up.
I see. Okay.
Oh, so um, what's next? Oh
You-
yeah. So another so another thing that we generate, if we look at yeah. Going back to the graph, we do see a bunch of asserts checking that this value must be greater than or equal to some value and less than or equal some other value. And those are the runtime asserts that we put into the graph to show to show the assumptions that we made while draft exporting. Um, okay, so now going to the second part, which is with custom operators. Um, while we're exporting, draft exporting, we will also record a profile. I'm getting kicked out of my room.
Oh, okay.
Let
Uh,
me, I'll go find another room.
okay. All right.
So, at this, while we're draft exporting, we also record a bunch of profiles for all of the operators that do not contain metakernels. And so what this looks like is, or this is stored in ep.report.op profiles. Um, so what this looks like is it's a mapping of the custom operator that does not contain that does not contain a meta kernel, and a set of profiles for what are the types of inputs and outputs that can occur. And so we can actually save this to a file from and then load it up later, but we can load it up even. So we can save this profile to a YAML file and it looks something like this. So it says for the inputs to this preproc, we found a tensor of rank 1 with D type 7. 7 I think corresponds to like float 32. And for this type of input, which is one tensor of rank 1 with a D type of float 32, it returns an output tensor of rank 1 and also D type of float 32. And so with this profile, we can then use it to generate a fake tensor profile for a fake kernel for us, so that every time we see a tensor input of this profile, we will also return an output of this profile. And this will allow us to generate fake tensor kernels for you so that you don't have to write it yourself. What this looks like is we can load this YAML file, and then with this unsafe fake kernels generator, we can then call export again, and it should run successfully. Oh wait, actually first, we should probably fix those errors.
Yeah.
So let's let's fix these data dependent errors. And in that case, if we run this code again, you run this code. Oh, sorry. Okay, so if we run export again, without this registration here, we see that there's no fake info registration. But if we load up the profile and then add this context, this will, based on this YAML file that we stored, it will load up a bunch of profiles. And then with this decorator, it will temporarily register fake kernels with this profile. So if we do this, then it will register a fake profile. Oh, I didn't print the exported program. And then we now get a graph with export. So in this case, if you are too lazy to write your own fake tensor implementation, with draft export, you can just save the profile that it returns and then load it and continue running and continue like exporting.
Yeah.
So this profile is specific to what is encountered. So if we pass in a tensor of rank 2 now, this profile will error because it has never seen the kernel output of type 2. So to fix that, we can either like manually append to this YAML file, or we can call draft export again with a new profile, and it will generate you a new profile here.
So if it encounters different shapes, then what happens? Does it try to make a kernel that has dynamic shapes in it, or?
It will error.
Okay.
But draft export will try to make you a new kernel.
So what will happen? Will you generate multiple kernels that are all specialized to their own inputs, or?
It will generate one kernel that contains like multiple of these profiles,
Okay.
and then it'll just like case match based on the profiles. But so this way of like generating fake kernels is not entirely accurate, because if you have data dependent behavior, like, oh, if my input of rank 1 then returns something of like rank 1 times 5, like, and then, or sorry, like if you have a value inside of the tensor and then you return a tensor of that shape, that specific shape, like, or that rank, like that could not work in this case, because it like hard codes based on like what rank you've seen and what rank you see in the input and what rank you see in the output.
All right. Makes sense.
Cool. Um, Yeah, so for some future work, we'll continue to get feedback and export errors and try to improve the report with more information, also to support more errors. And we will also work on improving the slowness of draft export. Because it is running the real tensors at the same time, there is some slowness. So that is something we'll continue to work on. So please try it out and let us know what you think and file issues to GitHub.
Nice. All right. So thanks, Angela, and yeah, please, I echo Angela. Please try it out. This is pretty cool, and a bunch of our internal users are already getting a lot of joy out of it. All right, we'll end here for today. Thanks. Bye bye.
Thank you.